Hello, today we're going to discuss how insertions and rotations work in AVL trees. I'm sure you're all familiar with binary search trees, so I'm going to discuss what they are very briefly. Binary trees consists of a finite set of nodes which should either be an empty set or consists of a root with left and right subtrees. Insertion is very simple and relies on the value of nodes that you want to insert and the number of nodes that are already inside the tree. Let's demonstrate it. Shown is a root with a value of 20. Let's insert a node with a value of 30. First, I will check if the value is greater than or less than the root. Since 30 is greater than 20, I will insert it in the right subtree. Now let's add a node with a value of 10. Let's check the root. Is 10 greater than or less than 20? Since it is less than, I'll insert it on the left subtree. Now let's see how to insert nodes into a BST that contains multiple nodes. Let's use the same example. Now I want to insert a node with a value of 25. First, check the root. Is the input less than or greater than the root? Since 25 is greater than 20, move down the right subtree. Next, check the root of the right subtree. Is the input less than or greater than? Since 25 is less than 30, 25 will be placed on the left subtree of the node. Now let's try to insert a node with a value of 15. Again, check the root. Since 15 is less than 20, move down the left subtree. Check again the node. Since 15 is greater than 10, move down the right subtree. Now that we know how insertion works, let's move on to AVL trees. AVL trees are self-balancing binary search trees. To see if a binary search tree is balanced, we have to check the balance factor. The balance factor for each node depends on the height of its left and right subtrees. As seen in the equation, the balance factor is equal to the height of the left subtree minus the height of the right subtree. If the balance factor is equal to -1, 0, or +1, then it is considered balanced. But if it is less than -1 or greater than +1, then the node is considered unbalanced. Now let's try to get the balance factor of each node in this BST. Let's check the balance factor of A. Since the height of its left subtree is only equal to 1, put down 1. Now let's get the height of the right subtree. Since its height is equal to 2, we subtract 2 from 1 to get -1. Now we label node A with having a balance factor of -1. Now let's check B. Since B has no children, we can say that its balance factor is equal to 0. Let's check the balance factor of C. Let's go to its left subtree. Since its left subtree only has a height of 1, we put down 1. Now, we check its right subtree. Since its right subtree has a value of 1. Now let's check D and E. Since D has no child and E has no child, we can say that they both have balance factors of 0. Now let's try to insert this node. Let's check the balance factor again. Since the height of the right subtree of node A was increased by 1, we can say that A has a balance factor now of -2. This means that node A is now unbalanced. And to balance the node, we perform what we call rotation. There are two basic kinds of rotation, left and right rotation. Let's look at left rotation first. In left rotation, from its name, we rotate left. In this example, we bring down 2 and we bring up 3. The letters pertain to subtrees with equal heights. Notice how C breaks off from 3 and attaches to 2. Let's move on to right rotation. In this figure, again, we want to bring down 2 and bring up 3, just like in left rotation. Again, you can see how C breaks off from 3 and attaches to 2. Now, we're going to see when to use what kind of rotation. First, we check the balance factor. If the balance factor of a node is positive 2, this means that the left subtree is greater than the right subtree. For this, check the balance factor of the left child. If the balance factor is equal to positive 1, perform a right rotation. But if the balance factor of the child is equal to negative 1, perform a left-right rotation. A left-right rotation, from its name, is a left rotation followed by a right rotation. As you can see, after a left rotation, the balance factors become positive 2 and positive 1. Now perform right rotation to balance out the tree again. Now, if the balance factor of a node is negative 2, that means that the right subtree is greater than the left subtree. Now check the balance factor of the right child. If the balance factor is equal to negative 1, perform a left rotation. But if the balance factor of a child is equal to positive 1, perform a right-left rotation. Again, a right-left rotation is a right rotation followed by a left rotation. Let's look at this example. Given the following nodes, perform insertion and rotation and balance the tree. First, we insert tree and check its balance factor. Since it has no child, its balance factor is equal to 0. Next, insert 4. Since 4 is greater than 3, we put it on the right subtree. Again, let's check the balance factor of each node. Since the height of the right subtree of node 3 is greater than its left subtree, its balance factor is equal to negative 1, and 4's balance factor is just equal to 0. Now insert 8. Since 8 is greater than 3, move down the right subtree. Since 8 is greater than 4, move down again the right subtree. Again, check the balance factor. Balance factor of 8 is 0, 4, negative 1, but this time the balance factor of 3 is negative 2, indicating that it is unbalanced. Since the balance factor of 3 is negative 2 and the balance factor of 4 is negative 1, we perform right rotation. Again, we check the balance factors. Now all the balance factors are equal to 0, indicating that it is balanced. Now we insert 6. Since 6 is greater than 4 but less than 8, we put it on the left subtree of node 8. Again, we check the balance factors, but this time everything is still balanced. So we move on to the next node. We insert 7 by putting it on the right subtree of node 6. Let's check the balance factors. 4 has a balance factor of negative 2, 8 has a balance factor of positive 2, 6 has a balance factor of negative 1, and 7 has a factor of 0. As you can see, both 4 and 8 are in balance, but since 8 has a higher level than 4, we will balance 8 first. As you can see, 8 has a balance factor of positive 2, while 6 has a balance factor of negative 1, so we use left-right rotation. After checking the balance factor, the tree is now balanced. After inserting 5, the balance factor of 4 becomes negative 2, and the balance factor of 7 is positive 1, so we use right-left rotation. Just like from our example, notice how 5 breaks off from 6 and attaches to 4. And again, the tree is now balanced. Yay! After inserting 2, the tree is still balanced. Lastly, we insert 1. But now, there are 3 nodes with a balance factor of positive 2. But since 3 has the highest level, we balance 3 first. 3 has a balance factor of positive 2 and 2 has a balance factor of positive 1. So we perform right rotation. After checking the balance factor of each node, we finally have our balanced tree. To summarize, to perform insertion and rotation, just check the value of the balance factor of each node. Thank you for watching, and I hope that you learned a lot from this video lecture.